when there is a situation where the work done by non-conservative forces is zero, then the principle of conservation of mechanical energy holds true. The principle of conservation of mechanical energy pretty much says that the final mechanical energy is equal to the initial mechanical energy, meaning the total amount of mechanical energy in a system stays the same. Now, there are two situations in which the principle of conservation of mechanical energy is true. If we evolve and come into a situation where we just ignore all the non-conservative forces, then the conservation of mechanical energy is true. The conservation of mechanical energy is true also, so not there can be non-conservative forces, but if the non-conservative force is perpendicular to the actual movement, meaning the work non-conservative, which is equal to the force of the non-conservative times cosine, it's the displacement times cosine of 90 degrees. If the non-conservative force and the displacement are perpendicular to each other, the work non-conservative is zero, meaning the conservation of mechanical energy is true. So just because there's a non-conservative force doesn't mean that your final mechanical energy is not going to equal your initial mechanical energy. Whenever this happens, it makes the problem much, much easier to solve and saves us a lot of hassle. When mechanical energy is conserved, the total mechanical energy in a system stays the same. So imagine you have this bobsledder, he's at a certain height, and he's starting from rest, meaning his kinetic energy is zero. He's at a very, very high point, so he has a total potential energy of 600,000 joules, meaning if we add his kinetic energy and potential energy, we have 600,000 joules. As he starts making his way down the path, his potential energy starts to decrease. If mechanical energy is conserved, the amount of potential energy you lose, which in this case was negative 200, that's going to be equal to the amount of kinetic energy you gained. And in the end, you still end up with the same mechanical energy throughout the entire trip. So throughout the entire trip, as he starts making his way down the hill, his potential energy gets smaller and smaller, and eventually all the potential energy he started off with becomes mechanical energy. If you run into an example for that, you realize you started with 600,000 joules of potential energy, and then at the bottom you find out that let's say you only found 500,000 joules of kinetic energy. Not all the potential energy became kinetic energy. The reason for that is because there must have been a non-conservative force that was removing energy, something like friction. So this is how to tell if something, sometimes if there's a non-conservative force acting on a system, if the total mechanical energy at the end isn't equal to the total mechanical energy at the beginning. So here we have an example of a motorcyclist is trying to leap across a canyon by driving horizontally off a cliff at 38 meters per second. Ignoring air resistance, find the speed with which the cycle strikes. If we ignore air resistance, we're going to assume that the work done by the non-conservative force is zero because there are no non-conservative forces, which means the final mechanical energy is equal to the initial. So if we set it up as an equation, the final mechanical energy is equal to the final potential energy plus the final kinetic energy, and the initial mechanical energy is equal to the initial potential energy plus the initial kinetic energy, because remember, mechanical energy is K plus potential energy. Some of the variables that were given to us, we know that his initial velocity is 38 meters per second. They tell us that his initial height was 70 meters from the picture. His final height is 35 meters. And that's about all we're given. Now, we're not given the mass, but that doesn't matter because when we set up our equation, we realize that we can end up canceling all our mass. We end up here. From there, we can rearrange our equations to stand for VF, and then we can actually plug in our values. We plug in 9.81 for G, we plug in 70 meters for our initial height, 35 meters for our final height, and our initial velocity, which is 38 meters per second, we can plug in. And when we plug that in, we can find out that the final velocity when the motorcyclist ends up landing on the ground is equal to 46.2 meters per second. So here we have another example. This time, this example has a non-conservative force, tension. But we find out that we can still solve it using conservation of mechanical energy, and we'll see why. It says the person starts from rest with the rope held in the horizontal position. He swings downward and then lets go of the rope. Three forces act on him: his weight, the tension of the rope, and the force of air resistance. It asks you, can the principle of conservation of energy be used to calculate his final speed? And the answer is yes. The reason you can use conservation of mechanical energy, because in this example, his velocity is pointing at the same point of his displacement. So at this point, his displacement is moving this way. His displacement is perpendicular to the non-conservative force, which would make it the work done by it zero. This is also true when he is here. The tension is pointing up. The displacement is pointing perpendicular. So throughout this entire ride, the work done by the non-conservative forces is 0 joules, which means we can treat it like conservation of mechanical energy. So we can assume the initial mechanical energy is equal to the final mechanical energy, and we can solve it the same way we did with our last problem. So we know that our initial velocity was 0 because he started from rest, and if the problem had actually given us a height, we would have been able to find out what his final velocity is. Or if they gave us his final velocity, we would have been able to calculate from what height he fell from. So here we'll do another example. It says we have a King Kai, is a giant among roller coasters. Located in Jackson Township in New Jersey, the ride includes a vertical loop of 127 meters. Suppose that the coaster had a speed of 6 meters per second at the top of the drop, neglecting friction and air resistance, and find the speed of the riders at the bottom. So this is telling us that there is a vertical drop of 127 meters. So if we wanted to, we could assume that our initial height is 127 meters. Our final height is 0 meters. They also tell us that the coaster has a speed at the top, so the initial speed is 6.0 meters per second, and we want to find the final speed. So we can pretty much, since we're ignoring wind resistance, we're going to assume that the work done by non-conservative forces is 0, because there are no non-conservative forces. So that means we can state that the initial mechanical energy must equal the final mechanical energy. So we can calculate that the kinetic energy initial plus the potential energy initial is equal to the kinetic energy final plus the potential energy final. Since we're assuming that the final height is 0, we can not worry about the final potential energy because it's going to be 0. So we can start plugging things in. 1/2 mass times the initial velocity, which they said was 6 meters per second squared, plus the mass times 9.81 times the height, which at the beginning was the initial height was 127 meters, is equal to 1/2 mv final squared. So just like before, we can cancel out the masses. If we wanted to, we can multiply everything by 2, so we get 6, or we could just actually just solve through it. If we solve this, I'm assuming we did the math correct, we'd find out that the final velocity is equal to 49.98 meters per second. We could have solved this problem also using our kinematics. We would have said that our initial velocity is 6 meters per second negative, because the velocity is pointing down. So our initial velocity is negative 6 meters per second. Our displacement in the y, or just we can even say just displacement in total, we can call it x or delta x. Our total displacement is equal to negative 127 meters. And our acceleration, we will set it as negative 9.81 meters per second squared. So we would end up using our Vf squared equals V initial squared plus 2ax. So we rearrange it, and our V final is equal to the square root of our V initial squared, which is negative 6 squared, plus 2 times negative 9.81 times negative 127. And when we solve through all that, we end up realizing that R equals 50.27 meters per second. Now, this isn't exactly the same answer we got before, because in realization, now that we checked these numbers, the last answer we forgot one simple thing. In the last problem, when I was calculating the initial kinetic energy, which if you remember was 1/2 m6 squared, and we cancel out the m. I forgot to square the 6, which counts for the small change. But if we had done the math right, we would have gotten the same answer just using kinematics. The main thing you have to realize from this is that when an object, when there are no non-conservative forces or work being done in an object, the final velocity of an object is pretty much the same as its velocity if it was in free fall. The only difference is during free fall, your velocity is focused downward, but without it, the velocity might be moving at a different direction. But the velocity ends up being the same, it's just pointing in a different direction. The magnitude doesn't change.